I'm Connor Smolinski, and this is our Introduction to Spectrophotometry presentation. We'll be going over the purpose of the presentation. We'll introduce spectrophotometry, and we'll give some definitions and equations that pertain to the experiment. We'll go over a concise summary of the experimental our results. We'll go over tables and figures with some sample equations thrown in, and our final conclusions regarding the discussion section and our references at the end.
We also determined the absorbance of COCl2. We created a spreadsheet and a standard curve with the data we obtained. And with the data obtained throughout the experiment, we also used it to determine our unknown concentrations.
The first definition that we'll go over is spectroscopy, which is entails the identification of properties using the absorbance spectrum. Spectrophotometry, it uses light radiation to determine the amount of the substance that is present, and it does this by the amount of light. The amount of light that is absorbed depends on the substance that's involved, and the absorbance is measured using percent transmittance. And this pertains to
Beer's law, which is A equals E times C times L. We measured the higher the concentration, the less light was absorbed, and E was molar absorptivity. C was a molar concentration of substance, and L was the path length, which is like how far the light would travel through the solution.
And this graph here just shows the correlation between concentration and absorbance, as they're directly related to one another. So as one increases, so does the other, and that's pretty much the whole concept of the law. Absorbance can be specifically found using this equation, where A equals absorbance, which equals 2 minus the log of the percent transmittance, where percent T is the percent of the light that goes through the substance. And both the equation for Beer's law and this equation were essential in finding the absorbances for our experiment.
How we started out is we had 2 microvets. Then we split the spec 20 at 400 nanometers to start out with. One cuvette was 3/4 of the way filled with deionized water, and the other one was filled 3/4 of the way with COCl2 at 0.150 molar. We zeroed the spec 20 with the water cuvette, and then what we did is determine the percent transmittance and absorbance. We put the water blank in the spec 20, zero it, and we put the COCl2 in there to determine the percent transmittance and absorbance at 400 nanometers to 600 nanometers with 25 increments. And that's how we determined our limit max, from looking at the lowest percent transmittance and the highest absorbance within the tables.
We made a dilution set using 8 test tubes. The first tube was 5 milliliters of water, and then the tubes 2 to 7 were the dilutions, which were composed of a total of 5 millimeters of fluid. And then our final tube was just straight COCl2. And yes.
We then blanked the spec 20 again with a water blank. The concentration determined through using the molarity equation was MC times VC equals MD times VD. Standard curve we created using this data, and this just showed the relationship between the wavelength and the absorbance.
From the standard curve, we found our best fit line, which was that, and we used this equation to determine the concentrations of our unknowns.
Here is a table that we recorded that in. This is showing the construction absorbance spectrum of COCl2. This just gave us pretty much our absorbance and the transmittance from 400 to 600 nanometers. And as you can see, the limit max we predicted to be 500 because the percent transmittance was the lowest in its column at 17. And the absorbance was 0.772, which is the highest in its column, which gave us our limit max of 500 nanometers.
This is our example absorbance problem. We use the absorbance equation, A equals 2 minus log% transmittance, to determine the absorbance for test tube number 3 to be 0.0757.
Here's another graph, the standard curve. This just showed the relationship between wavelengths and absorbance from 400 nanometers to 600 nanometers.
This is our table 2, which shows the concentration, percent transmittance, and the absorbance for our dilution set. Our dilution values are on the side, the left side there, and our concentration, percent transmittance, and absorbance are shown on the right.
We use example molarity calculations for test tube 3. For that we use MC times VC equals MD times VD. MC was just the molarity of the CaCl2. VC was how much of the CaCl2 we added to the diluted solution, which is 2 milliliters in this situation. We solved for MD, and the total, and VD was the total amount of dilution, so it's 5 milliliters. And we solved for MD for test tube 3, and it was 0.0600 molar. We had an example E calculation for test tube 3, and we solved for E. 0.328 was the absorbance for test tube 3. 0.0600 molar was the molarity for it, and 1 centimeters was the path length, how far the light was traveled through the solution, which was a given to us. And E was 5.47 liters divided by milliliters times centimeters.
This figure represents the standard curve that we formed using our dilution set. And from this, we determined our best fit line, which turned out to be y equals 4.6361x plus 0.0138.
This is table 3, determination of concentration of our unknown solutions, and this is at lambda max 500 nanometers. Here's unknown number 12, which is the percent transmittance was at 36 with the absorbance at 0.446, and unknown 13 was 31.6. And absorbance at 0.500.
This is a calculation of our first unknown number 12, where we took the y equals mx plus b and converted it to the Beer's law equation. And we substituted our values in for that and got a concentration of 0.0932 molar.
Here's the equation for unknown number 13, the same steps, just plug in the different absorbance and transmittance, and we got a concentration of 0.150 molar, which is a mistake.
We had a typo on this slide, so we'll fix it. Our discussion section for question number 1, the percent transmittance and absorbance had an inverse relationship. As the percent transmittance decreased, our absorbance increased. An example of this would be test tube number 1. Our percent transmittance was 99.4 at our lambda max, and our lambda max was 0.00300. And for test tube number 2, our percent transmittance was 69.4, and our lambda max absorbance was 0.158.
The data did support a lambda max of 500 nanometers. Table 1 was the highest absorbance at 0.772. Unknown concentrations fell on the linear regression line in figure 2.
For our third question, the absorbance and concentration had a direct relationship. As the concentration increased, so did the absorbance. And this is shown in our test tube number 6, where the concentration was 0.105 molarity and the absorbance was 0.410. In test tube number 7, the concentration was 0.12 molarity and the absorbance was 0.506.
It did support Beer's law for question number 3. Our unknown 12 was 0.0932 molar, and for unknown 13 it was 0.105 molar.
So for our final question, the purpose of this experiment was to determine the lambda max of CaCl2 and we found that lambda max to be 500 nanometers. We determined our unknown 12 to be 0.0932 molarity and our unknown 13 to be 0.105 molarity.
These are our references.
That's our report, so thank you.
Thank you.